So now we understand a bit about the theory of integration, and we also understand that integration is the reverse of differentiation. They're inverse processes to each other. This means we can go about finding integrals by comparing them with derivatives of functions that we know about. But in general, it's actually quite difficult to integrate. One has to find tricks and things like this in order to find integrals. And in fact, it may surprise you to know that most functions that you write down can't be integrated. By contrast with differentiation, for differentiation, you can always find a derivative. For integration, it may not be possible to write it in terms of elementary functions. Consider these examples. First is the error function, the integral of e to the minus t squared. That doesn't have an algebraic expression that you can write down in terms of elementary functions. Similarly, cos t squared and cos of sine t, all of these can't be written down in terms of elementary functions, but they're nevertheless very important functions and define higher classes of functions that you'll learn about in future years. However, some integrals can be integrated, and we're going to concentrate on those. Usually you need to use tricks, and one of those tricks is the substitution rule. Let's have a look at that first. Our starting point for the substitution rule is to consider the chain rule for differentiation and integrate it. So consider the following. If I differentiate a function, capital F, of g of x, then I can differentiate this using the chain rule quite straightforwardly, and that means I can integrate it using the fundamental theorem of calculus to tell me that. So what this is telling me is that if I have a function of some other function times a derivative of the other function, then I can find the integral of this whole expression. It's a bit difficult to see how that's going to work, but if I just do the following, if I let the variable u equal g of x, then g prime of x is equal to du by dx, and therefore du is g prime of x times dx, where I use a rule for differentials to multiply up by the dx. Therefore, this complicated looking integral is actually the integral of the derivative of f of u du, which I can then integrate. So that's the theory behind it. How does it work in practice? Let's try a couple of examples. Let's look at the integral of cosine x times e the power sine x. Now, the first thing to note is that cosine x is a derivative of sine x, so that's our first clue that using the substitution rule might be useful. Let me write u equals sine x, which implies, because du by dx cos x, du is cos x dx. Now, the important thing of what I've done here is when I've got cos x dx, I know that that's going to correspond to the dx in here and the cos x in here, while the sine x in the exponential is given by the variable u. So therefore, I can write the integral, we call this I for shorthand, the integral I is therefore the integral of e to the u, and the cos x dx becomes just du. And in terms of the variable u, this is a really easy integral. It just gives me e to the u plus a constant. Resubstituting for u, I know that this is e to the sine x plus c. And a simple check by differentiation will reveal that this is the correct answer. So that's the first straightforward example of integration by substitution. The key thing was to realize that the cosine is the derivative of this sine here. Let's try a couple more. Let's consider the integral of x squared over the square root of 1 minus x cubed. How can I use substitution here? Well, if I note that the derivative of the 1 minus x cubed part is just proportional to x squared. That's the first clue in order to use the substitution rule. So I let u equal 1 minus x cubed, then du is minus 3x squared dx. So the integral then becomes, the integral, we have 1 over the square root of u times x squared dx is minus 1 over 3 du. So this then becomes minus 1/3 u to the 1 over 2 times 2 plus a constant, which is equal to minus 2 over 3 times the square root of 1 minus x cubed plus c. Here's an example where it's not immediately obvious of how to use substitution. Where would we use substitution in an example like this, since there's only one function? Well, let's remember that the definition of tan is sine over cos, and suddenly we have two functions, one of which is a derivative of the other. So in order to use a substitution, what we're looking for is to link up the dx with some other part of the function. And in this case, the dx will link up with the sine x, and that I want to be du. So I let u equal cos x, so du is minus sine x. And then in the integral, I can substitute for these two things, and that leaves me with minus 1 over u du, which is minus log u plus c. And in fact, integrating 1 over a function gives me actually the log of the absolute value. So this is then minus log absolute value of cos x plus c. So that's it for indefinite integrals. What about for definite integrals where limits are given? Well, one way to tackle that is just to calculate the indefinite integral and then do the limits later. That's fine. But you can do it straight away if we note the following. If we integrate from a to b, f of g of x times g prime of x dx, and I'm rewriting that in terms of u, then this is the integral of f of u du as we've seen before, where little f is equal to capital F prime, and the limits now become g of a and g of b. Now the reason for this is because we let u equal g of x, so du is g prime of x dx. That implies that when x equals a, u is equal to g of a, and when x is equal to b, u equals g of b. And since we're integrating with respect to u, I need to write these limits in terms of u. Let's try a final example using this. The integral from 0 to pi by 8 of sec 2 theta tan 2 theta d theta. The key thing to note here is that the derivative of sec is sec times tan. So if we let u equal sec 2 theta, du is 2 sec 2 theta times tan 2 theta d theta, which is actually just the integrand. The integral then becomes, nice and easy, 1/2 du. Couldn't be much simpler. Now, what about the limits? At theta equals 0, u equals sec 0, which is equal to 1, and at theta equals pi by 8, u is equal to root 2. So going back to the integral then, and that's then just a simple integral to work out. There are actually other ways to do substitutions to solve integrals. Very often integrals require you to stare at them for a bit in order to see what these sorts of substitutions are. One class of these is inverse trigonometric substitutions. Let's just see an example of this in practice. So let's say we want to find the integral of the square root of a squared minus x squared. Now, we can't do this using the other substitution method that we've just looked at, but if I remember that cos squared plus sine squared is equal to 1, we can actually use that to find the integral as follows. If we let x equals a cos theta, then dx is a sine theta d theta. And notice we've framed this substitution in a different way from before. We've actually got dx in terms of d theta rather than the other way around. Now I can substitute directly for x and directly for dx in terms of theta, and then what does this integral then become? Well, the integrand becomes the square root of a squared minus a squared cos squared theta, and the differential dx becomes a sine theta d theta, and we have a minus sign from the dx. So dx is minus a sine theta d theta. Now the limits, when x is equal to 0, theta is pi by 2, and when x equals a, theta must be equal to 0. So the limits then are pi by 2 to 0. And let's simplify this integral in order to evaluate it. The square root part, we can use a substitution that 1 minus cos squared theta is sine squared theta. Taking the square root, that gives us another sine theta. So this becomes the integral of a squared sine squared theta d theta. Now what about the limits? Well, let me swap them around. The minus sign I can swap with the limit ordering. minus the integral from pi by 2 to 0 is the same as the integral from 0 to pi by 2. And now in order to do this integral, I can use a half angle formula for sine, which I'll just quickly look up. So this is 1 over 2, 1 minus cos 2 theta d theta. Now integrating this term by term leaves me with a squared times pi by 4. So that's another way to use substitution to solve integrals. And you'll find that different types of substitutions come in different ways. So you can do the same sort of tricks for inverse hyperbolic trig functions and so on. Very often it can be quite difficult though to see which substitution to use, so it requires quite a lot of practice.